Okay, let's solve the next problem, problem 29. In problem 29, we have a spaceship, the Daedalus, orbiting too close to a star. So the hull is deteriorating, the ship is about to be destroyed. We have two options to save the ship. One, we can repair the shields, which will offer additional protection, but leave us in place. Or, option two, we can repair the sublight engines and move out a certain distance away from the sun. But doing this will come at the price of not having the additional protection from the shields. So our job in this problem is to figure out which option the crew of the Daedalus should choose. So in part A, we're asked, what is the temperature of the environment where the ship currently is? So we're told that the power absorbed by the Daedalus at this point is 1.0 times 10 to the 13 watts. The emissivity of the Daedalus is 1. The cross-sectional area of the Daedalus is 18,750 meters squared. So from here, we're asked to solve what the temperature of the environment around the Daedalus is. So you should know that we should use the Stefan's law here. So power absorbed equals sigma, the Stefan-Boltzmann constant, times the emissivity, times the area, times temperature of environment to the fourth power. And remember, sigma is 5.67 times 10 to the negative 8 watts per meter squared Kelvin to the fourth. All right. So we know everything here except for the temperature of the environment. So let's solve for that. Temperature of the environment, power, is going to be P absorbed, sigma E. Okay, right. And now we need to take the fourth root. Remember, this is temperature environment to the fourth power. In other words, to the fourth, we take the fourth root, so the opposite side of the equation is taken to the 1/4 power. So let's plug in our numbers. 0.0 times 10 to the 13 watts divided by 5.67 times 10 to the negative 8 watts per meter squared Kelvin. Right. Squared Kelvin fourth. Multiply that by emissivity, which is 1, and cross-sectional area, which is 18,750 meters squared. And this whole thing taken to the 1/4 power. So we end up having our environmental temperature equal to 9,848 Kelvin, which is the same thing as saying 9.8 times 10 to the 3 Kelvin. And that's how you solve part. Now part B is asking us this question. Suppose we move from position 1 to position 2. So in other words, what if we fix the sublight engines? What would be the power absorbed at this position, at this distance from the sun? So we're told that at this position, the temperature is 5,000 Kelvin lower than at position 1. So in other words, the temperature of the environment here will be the temperature of the environment that we just calculated, minus 5,000 Kelvin, because we're dropping by 5,000 Kelvin. So our new environmental temperature is 4,848 Kelvin. And again, our cross-sectional area is the same, our emissivity is the same. So again, we're going to apply Stefan's law. P absorbed 2 equals sigma times emissivity times cross-sectional area times temperature from the environment to the fourth power. So go ahead and plug in our numbers here. Times 1 times 18,750 meters squared times 4,848 to the fourth power. And if you plug and chug those numbers, you will get a number of around 5.9 times 10 to the 11 watts. And that's how you solve part B. Okay, let's solve part C. So in part C, we're asked, which system should the Daedalus crew fix? Should it be the shields or the sublights? Again, if we fix the shields, we'll get added protection, but we'll be stuck where we are. If we fix the sublights, we can move away a distance, but we lose the additional protection of the shields. So the question is, which one should we fix? Which option will save the ship? Well, the way to answer that is to figure out how much power the ship can absorb with the shields at point 1, and how much power the ship can absorb without shields at point 2. So we know that power absorbed in position 1 is 1.0 times 10 to the 13 watts. Power absorbed in position 2 is 5.9 times 10 to the 11 watts. So, now we've got to figure out how much can the ship withstand at position 1, how much can the ship withstand at position 2. Well, we're told in part C that if we fix the shields, the ship can withstand 1.0 times 10 to the 14 watts. And then we're told shields. If we fix the sublights, you can withstand 1.0 times 10 to the 9 watts. So notice, this is greater than the power absorbed at position 1, while the power that the ship could sustain at position 2 is less than what it would face. So therefore, the only way to save the ship is to fix the shields. Okay, let's solve problem 32. In problem 32, we have a mass of ice, 100 kilograms, that has been heated to a temperature of 0 degrees Celsius, or 273.15 Kelvin. In the problem statement, we were given the latent heat of vaporization for H2O and the latent heat of fusion for H2O and the latent heat of vaporization for H2O. So in part A, we were told that 4/5 of the ice has been melted. So we're in the middle of a phase change. And we're asked to find the heat required to melt 4/5 of the ice. So how do we do that? Well, I'm going to use the latent heat equation. So the heat required to melt 4/5 of the ice is going to be equal to the mass of the ice melted times the latent heat of fusion. So remember, you use latent heat of fusion when you're going between solid and liquid, liquid and solid, and you use latent heat of vaporization when you're going from liquid to gas, gas to liquid. Okay. So the ice melted here is 4/5 of the total. Put in here 4/5 times 100 kilograms times the latent heat of fusion. And then, plugging all these numbers in, we end up with 2.67 times 10 to the 7 joules. Now in part B, we are asked to find the change in entropy of this system. So in this case, you want to use the change in entropy equation, which would be delta S is equal to the heat over the temperature. So our heat, of course, is 2.67 times 10 to the 7 joules. Our temperature here is the temperature the ice is currently at, which is 0 degrees Celsius. But we have to be careful here, because if I divide it by 0, that would be a big problem. So I need to use the temperature in Kelvin to find the change in entropy. So our change in entropy will be 9.78 times 10 to the 3rd power joules per Kelvin. And that's how you solve part B. C. So in part C, we're asked to consider what would happen if the heat that was used to melt the ice was instead the heat from a hot reservoir in a heat engine. So we're given the efficiency of the heat reservoir, we're given the efficiency of the heat engine, 20%, and we're asked to find what the work done by the heat engine would be. So remember our efficiency equation. So efficiency of the heat engine equals work done by the heat engine divided by the heat from the hot reservoir. So remember, what we get divided by what we pay for it. So in this instance, we want to find the work. So the work done is equal to the efficiency times the QH. Efficiency here is just 20%, which is the same thing as 0.2. QH, we already found what that is. That is 2.67 times 10 to the negative 7 joules. And so we end up with a work of 5.34 times 10 to the 6 joules. And that's how you solve the problem. On to the next problem, problem 31. So problem 31 is probably the hardest problem on the test, and the one that the most people had trouble with. So let's set up the scene. So in problem 31, which is actually out of one of your homework problems in chapter 15, just slightly modified, we have 3 charges arranged in an equilateral triangle. So that means that the sides are the same length and that the angles are all the same. So 60 degrees here, 60 degrees here, 60 degrees here. The question asks us, we're given the charges for each individual charge. So we have a positive charge A, positive charge B, a negative charge C. And in part A, we're asked to find what is the magnitude and direction of the electric field at point B. So there's a couple ways to do this. I'm going to do this the simplest way. You could also do it by, you could find the force first and then go to the electric field. But I'm just going to go ahead and do it the electric field way. Alright, so we want to find the electric field at point B. So let's figure out what the electric fields of all these individual charges are at the position that the B charge is at. So first, let's figure out what the magnitude is of the electric field due to a charge. Okay. So remember, this is a magnitude. Our absolute value symbol over the charge. All right. So notice here that R in this case is going to be 0.500 meters. Because that's the length of the side. So that's remember, it's a radial distance from, squared. A radial distance from this charge to this charge. So let's plug in our numbers here. 8.99 times 10 to the power of 9. QA was 1.65 times 10 to the negative 6 coulombs. 0.500 meters squared. Meters squared per coulomb. There. Let's put this squared outside. All right, so go ahead and plug and chug our numbers here. And we'll end up with the electric field from A being 5.9, the magnitude, being 5.9 times 10 to the fourth power newtons per coulomb. Okay, so that's great. So we've gotten the magnitude of the electric field from charge A at the position where charge B is. But now we need to figure out the directionality. Okay, so first let's figure out what the x component of this electric field is. That's just going to be the magnitude of the field times the cosine of 60 degrees. So if we were to draw ourselves, let's go over here. If we were to draw ourselves a nice little picture here, where B is, and our 60-degree angle. This guy right here is our x component. This guy right here is our y component. So to get the x component, we need to use cosine, because cosine is cosine is adjacent over hypotenuse. So the x component is equal to the hypotenuse, in this case the magnitude of the electric field due to charge A, times the cosine of 60 degrees. Let's go ahead and write that down, and we get 2.97 times 10 to the fourth power newtons per coulombs. Let's do the same thing for the y component. In this case, we'd be using sine of 60 degrees. And that would be 5.14 times 10 to the fourth power newtons per coulombs. All right, and notice we're not quite done. Now we've got our components, so we need to write this in unit vector notation. I'm just going to make a little room here and write this down in unit vector notation. So E vector A equals, well, we've got the x component, 2.97 times 10 to the fourth newtons per coulomb, and that is an x hat, positive x hat, because the electric field from A will be directed in the positive x direction. And then plus 5.14 times 10 to the fourth power newtons per coulomb, y hat. And that makes sense because the x component is in the positive x direction, so it should be positive. Y component, positive y direction, everything's positive. So that is the electric field from A at point B. All right, let's consider the electric field from charge B. Well, in actuality, there is no electric field from charge B at the point where the charge is, right? The charge can't have an electric field on itself, right? Because the radial distance is 0. So this has got to be 0. There's no impact from charge B on the net electric field at its position. Right. Okay, so now that that's solved, let's move on and look at the electric field from C. So the magnitude of the electric field from C will be K, QC. Again, this is a magnitude, so we have to have our absolute value symbols over R squared. 0.99 times 10 to the 9 newtons meters squared coulomb. And this is an absolute value, so this will be 4.30 times 10 to the negative 6 coulombs. Divide that by R squared, 0.500 meters squared. We plug that in, and we get a magnitude of 1.55 times 10 to the 5 newtons per coulomb. Okay. So, same as before, let's draw a little picture here. Our charge B and charge C here. And notice the electric field will be going in this direction. Remember, the electric field flows into a negative charge, so it's going to be directed this way. So the y component is directed downward, and the x component is directed along the positive x-axis. So let's figure out what these components are. ECX, again, this will still use our 60-degree angle here. EC cosine of 60. And that gives us 7.7 times 10 to the 4 newtons per coulomb. We're going to get our y component, same idea, except now we're using sine. So this would end up being 1.34 times 10 to the 5 newtons per coulomb. So last but not least, we need to put this in unit vector notation. So E vector C is the x component, so it's 7.7 times 10 to the 4th newtons per coulomb x hat. But notice, again, we draw a little guy up here. The electric field is directed downwards, so that means that while my x component is positive, my y component is going to be negative, because the y component is directed down the y-axis. So, get minus 1.34 times 10 to the 5 newtons per coulomb y hat. All right, so now we've got both EA and EB in unit vector notation. Let's find the net magnitude and direction of this electric field. All right, let's figure out the net magnitude and direction of this electric field. So the net electric field is equal to the individual contributions from each charge. Again, we have discovered that the electric field contribution from B is 0, because it's sitting right there, so there is no electric field from B at point B. So let's add up these individual contributions. So we have EA, 2.97 times 10 to the 4th newtons per coulomb x hat plus 5.14 times 10 to the 4th newtons per coulomb y hat. So this is EA. So now we have to add in EB, or sorry, EC. So we have EA, now we're adding in EC. So this would be plus 7.7 times 10 to the 4th newtons per coulomb x hat minus 1.34 times 10 to the 5 newtons per coulomb y hat. So remember when we talked about unit vector notation, we add together the like unit vectors, so add together x hat and x hat, y hat and y hat. You can't add together x hat and y hat. Like you can only add similar unit, you can only add the same unit vectors. So we do this, we get final x component of 1.067 times 10 to the 5 newtons per coulomb minus 8.26 times 10 to the 4th newtons per coulomb y hat. So this is our net electric field in unit vector notation. But remember, we're trying to find the magnitude and direction. We need to find the magnitude number and the angular direction. But from here, it's easy. Okay, so we know that the net magnitude is just equal to the square root of these individual guys squared. So EX squared is this quantity squared. EY squared is this quantity squared. So we'll end up with E net being 1.35 times 10 to the 5th power newtons per coulomb. So this is the magnitude of our electric field. Okay, we found the electric field magnitude. Now let's solve for the direction. So look at this. This is point B. We know that the electric field magnitude is directed in this direction. So just so note, this would be the positive x-axis. So we know that the electric field is in this direction. So now angle theta right here. We know that the tangent of this angle, so tangent of theta, is going to be equal to EY over EX. Right? So, or tangent is TOA, opposite over adjacent. So then that means that theta is equal to the inverse tangent of EY over EX, which is the same thing as the inverse tangent. Let's plug in our numbers here of 8.26 times 10 to the 4th newtons per coulomb divided by 1.067 times 10 to the 5 newtons per coulomb. So the theta we get here is a value of 37.7 degrees. Note here, though, we have to be careful. Note that this is not 37.7 degrees above the x-axis. So if we do a little y-axis here, this would be 37.7 degrees above the x-axis, but note that is not what we have here. We have this guy right here. So the angle is 37.7 degrees below the x-axis. Below x-axis. You could have also written down theta equals 322 degrees from above the x-axis. So either of those would have been accepted. So that's how you solve the problem. Finally, let's solve part B. So in part B, we are asked to consider what would happen if I halved charge B. So I divided 6.85 microcoulombs by 2. So what would the impact be on the electric field at point B, and what would be the impact on the electric force? Well, remember from earlier that the electric field due to B at point B is equal to 0. It doesn't have any impact on itself. So therefore, the electric field, no matter what I do to charge B, will stay the same. Because we don't have that second Q in our electric field equation. That is not the case, however, for electric force. Remember our electric force equation, the magnitude, okay, Q1, or Q2 over R squared. So notice, let's say I put in A and B here, just for clarity. Notice the charge B term is in the electric force equation. So that means the electric force has to change. So the electric force will not stay the same. In fact, it will decrease by a factor of 2.